Okay, in this video we're going to determine the coordinates of every turning point and inflection point for this function. So let's go ahead and look at our first derivative. I guess before we do that we better get rid of our radical as always. So if we see a cube root, we can write that as power of 1/3, and we have x squared underneath that root, and then we still have subtract x. So our derivative, our first function before we get to the derivative is going to be 3 times x to the power of 2/3 subtract x. Now we're set up. We can find our first derivative and proceed to look for our critical values. So sidestep the 3, and then power comes down, subtract 1 from 2/3. Of course, is subtracting 3 over 3. That gives us a negative third power. And then we're left with a minus 1 if we differentiate minus x. And now, before we maybe start trying to look for critical values, it might be a good idea to recognize that that x has a negative power, so maybe we'll write that in the denominator. And of course, we can cross off those 3's and cancel those 3's, so we have 2. And then instead of writing x to the power of negative third, I think I will go back to a radical there, just to recognize that we can make our first derivative undefined by subbing in a 0 for x, and then we have 2 over the cube root of 0, which of course is undefined, and that's going to be a critical value. So maybe our easy critical value here, and that might not have been easy if you left that as a negative power, you might have missed it, but hopefully not. If you recognize your first derivative is undefined at x equals 0, that is your first critical value. So I think the harder critical value is trying to figure out what makes this equal to 0. So I'm tempted to go back to a negative power again, but I think we'll just kind of wrestle with the radical here. Might be a little bit more familiar. So we got to solve this equation, which is a little bit of a nuisance. But anyway, let's maybe add 1 to both sides. That's one way of dealing with this, possibly a little less efficient than working with a negative third power. But anyway, we can take the reciprocal of both sides or multiply both sides by the cube root of x. Might even actually make a little more sense. It's going to give us cube root of x. That's pretty messy. Let's go with the cube root of x times 1. And if I multiply the right by the cube root of x, of course it cancels. And then with inspection, you can probably recognize that the cube root of 8 is 2, so x equals 8 is our other critical value, or you can be a little more mechanical and cube both sides, and you get your second critical value that way as well. So our two CVs, critical values, are x equals 0, since our first derivative was undefined, and also x equals 8, since our first derivative was 0. And now we do our number line test and I guess sign diagram to figure out when our first derivative is negative and positive. So we'll put our two critical values on here, and I'm going to have to go looking for our first derivative. I guess it's sitting right there in front of me. Yeah, we can just maybe quickly rewrite that, or just visualize. Actually, I can slide it down here and visualize an f prime instead of that 0, but it might be a little safer just to do that. So if we put something like a -1, we'll just go to the left of 0 first, -1 into our first derivative. It's going to give me 2 over the cube root of -1, which is just -1, and then -1. I think you can see we get -2 minus 1. That's definitely a negative portion of our sign diagram here. So our first derivative is negative when x is to the left or less than 0, and that means our function is decreasing. And then we'll just keep testing 2 more regions. So in between 0 and 8, +1 works great. So if we put +1 in there, the cube root of +1 is of course 1, and then we have 2 minus 1, and we can see our first derivative is going to be positive between 0 and 8, which means our function is increasing. And then lastly, we put in something to the right of 8, and I might put in something easy to work with that cube root, like 27. And if you put in 27 for x, the cube root of 27 is 3. You can recognize that 2/3 minus 1 is a negative, so our first derivative goes back to negative. and we have a decreasing function. So maybe just model some possible tangents here. So maybe look at the 8 first, because we knew we have a definite horizontal tangent there because our derivative was equal to 0. So we knew we had a definite stationary point at x equals 8. And if our tangent slopes are going up to the left and down to the right, it's pretty obvious that we have a local maximum. And that happens at x equals 8 in the ordered pair. We'll worry about the y value in another minute or so. Over on this side, I can't model a horizontal tangent at x equals 0, because that's not necessarily a station point, because that didn't make our first derivative 0. It made it undefined. And if I see a sign change and I see an undefined slope, that tells me I'm dealing with a sharp point. So our tangent slopes are going down, and I'm expecting a sharp point or cusp of some sort at x equals 0, and then our tangent slopes go up again. And I think we can see that we have a local minimum contour happening at x equals 0. And then when we put 0 into this original function, this one's easy because there was x's in every term. So we know our local minimum is at the origin. And it might be worthwhile to go up and look at the original function again to confirm that. So if we plug in 0 into our function, maybe just do it here, we know that's going to output 0 because there's x's in both terms. And you can square 0 and take the cube root of 0, but guess what? You're still going to have 0. So that first term is guaranteed to be gone. And maybe since we can see the function here, let's plug in that other critical value to figure out what's happening, or where our local maximum is happening in terms of a y value. And this will be 3 times the cube root of 8 squared, which is 64, and then minus 8. So that's going to be 3 times 4. Cube root of 64, of course, is 4. So that looks like it's going to be 12 minus 8, or 4. So now we have the coordinates to our local maximum. So that's going to be 8 and 4. So I think that should be good enough. We have the coordinates. I guess I should box that, but it's in bright yellow ink, and I even stuck it there for with it. So I think it's pretty clear that we know both of our turning points, and we even wrote down the exact coordinates for them there as well. So now let's move on to our second derivative. We'll go back until we see a user-friendly version of our first derivative, and I guess we don't really have it. Closest thing I have is this, so I'll copy that, and then of course adjust that when we go down below. We can simplify the coefficient there. So let's move down, get ready for our second derivative. And there's our first. So we can clean that up a little bit. 3 times 2/3. Of course, that was just 2. I don't need that other bracket anymore. So here's our first derivative, kind of spaced out, but still does the trick. Now our second derivative is going to be sidestep that 2, and then the negative 1/3 comes down. Subtract 1 from negative 1/3, you will get negative 4/3, and then afterwards, when we differentiate that constant minus 1, it is gone. So similar, I guess, to our first derivative work, I think we'd be wise to write this as a radical. So I have a minus 2 on the top, and I'll just write it that way. That 3 is obviously on the bottom. And then instead of writing x to the minus 4/3, instead of writing x to the positive 4/3 on the bottom, I think we'll go back to our cube root due to the 3 on the bottom, of course. Once that x to the 4/3 is sitting in the denominator, that 3 is our index, and that means we have x to the power 4 underneath that cube root. If you can see that, hopefully. If you can't see that, hopefully you've heard that. Okay, so there's our second derivative, and if we try to make that equal to 0, that's not a good plan because it's impossible. You need an x in the numerator in order to make that any rational expression equal to 0. So all we can do is recognize that if I put 0 in for x, I clearly get an undefined second derivative. So that is our possible inflection point. And it's going to happen again at that origin. Now we already have a local minimum there, so is there any way our concavity could change? And think about that for a few seconds. You might be confused because if the concavity changes, it's going to be pretty tough to get to get a turning point there as well. So let's just maybe safely work with our second derivative. Plop in our, remember, don't call it a critical value, but plop in our possible turning point value. And then we don't have to do much here, because if I put in -1 or +1, keep in mind this is all raised to the power of 4. So any negative raised to the power of 4 is going to go to a positive. So we're guaranteed to have positive output once we take the cube root of x to the power of 4. So maybe more clearly, if you put x equals ±1 into your second derivative, you're going to get -2/3 both times. So that means, and I think this is good news, our concavity is down. Remember, if you're negative, you might be down. So don't be negative. Some life advice here. And I'm just going to abbreviate our concavity to concave down. We have a frowning function, and then after 0 we have a frowning function, so we definitely do not have an inflection point. So let's make sure we're crystal clear with that. Therefore, no IP for this function. So we could definitely go to decimals now and kind of wrap up and confirm our findings, but just to maybe be brave or possibly foolish, let's just quickly write down our function before we maybe cheat and use technology. And I probably should go back and check, but I think my memory will hold up here. This is our original function. Now what do we know? Well, I guess we know a couple of things. We know that we have 2 turning points. Let's get those maybe listed here first. So I guess those axes are straight enough. So at the origin we have a turning point. So that's that. And then let's just go over and put 8 somewhere here. And we notice that would be 4, would be the y value. So let's just put it there. So that's another turning point as well. So here's where I would ask myself, okay, which one of those was the min, which one was the max? Well, this was the min at the origin, and that's a maximum value. So we can probably take a guess as to how to connect those points, but we're not done yet. Let's consider our concavity as well. To the left of 0, this function was concave down. So let's just try to draw something that's frowning here. I think that does the trick. I won't go too far. So there's a function that's frowning, tangent line sitting on top. Now it might actually come back down again, but then as I hear myself say that, if it comes back down again, I would have found another turning point. So I know that function is going to be steadily going up if we go to the left, or maybe rephrase that. If we're going left to right, our function is always decreasing. So our y values are getting smaller from left to right, which means I guess if we go backwards, of course, they'd be getting bigger. So there's no turning points to the left of 0, and our first derivative told us that. And if I consider a concavity to the right of 0, this is another concave down. So I'm just going to go up to this point, at least half straight, and then recognize that I have to turn around and come back down. And that's pretty much everything that we found from our first 2 derivatives. So there's our local max. That was helpful information. We also have a local min. It was the strange sharp point, or cusp in this case. What else did we use? We used our concavity, of course, because we have a concave down section of our function, and then we have another concave down section of our function, I guess before and after 0 there. And the only other thing we could add would be our x-intercept, because if this thing keeps coming down, it's probably going to hit the x-axis. It would have to at some point. So maybe for some bonus marks here, we could set this equal to 0 and try to figure out how we would make x, what x values we would use to set our function equal to 0. So this has nothing to do with calculus. Everything to do with, I guess, working with radicals. So let's switch this back to a negative, sorry, not a negative, to a power of a positive 2/3. And then this is x to the 1. If we just do a common factor, we can actually predict our x-intercept as well, which means we could sketch this curve. And of course, I don't think we're doing, or at least I'm not doing as good a job as decimals here on the tablet, but I think the structural pieces and features are all intact there at least. So if we pull out the smallest of those 2 powers, of course, that's 2/3, x to the 2/3, and that would give me 3, minus x to the power of something. I just have to make sure that whatever I add whatever power I put here, it has to add to 2/3 to give me 1. So that would mean that has to be 1/3. And of course, it's very wise to check by expanding that out to make sure you didn't mess up the common factor there. So if I expand this out again, I see 3 times x to the 2/3, and I see minus x to the power of 2/3 plus 1/3, or just 1. And then we can use our zero product property. And I guess we don't need to write that out separately. Whatever makes, I guess we don't need to rewrite the whole thing again. Let's just take the 2 pieces. If x to the 2/3 can be 0, that's a possible x-intercept. And guess what? You already know that. That's our local minimum there at the origin. And our sharp point, I guess our other x-intercept has to be whatever makes 3 minus x to the power of 1/3 equal to 0. So if we add that x to the 3rd on both sides, and you recognize that that really is a cube root, or if you would rather just raise both sides to the power of 3, which of course is the reciprocal of that fractional power on x, we have x to the power of 1 equals 27. I'm not going to put a 1 there. You'll think I have a prime or something on it. Okay, so that would mean, and this diagram is definitely not to scale here. Maybe I can back up a little bit more. So if I want to go all the way over here without erasing everything, that this function is going to come down, and at some point, probably not right there, but it would hit the x-axis again, and that would be at 27. So I'll just extend that a little bit further. And since that diagram is pretty rough in terms of its shape, because it looks like we're around 15 or 16 there, but we'll label that as 27 and 0. So there's not much left to, I guess, to see in Desmos, but let's just have a look at Desmos and see what the function was supposed to look like, and I guess how close we came to sketching this by using our first and second derivative, and a little bit of bonus, I guess, x-intercept fun thrown in at the end there as well. Okay, this is kind of disappointing. There's nothing really to see here. We've actually figured out all of the main structural pieces to this function, and when we look at Desmos, other than, okay, that's what it was at least supposed to look like in terms of how quickly that function was going up here. But again, remember, I'm going backwards, so as we go left and right, which is the intelligent way of reading your function, going in the positive direction along your x-axis, we can see all these y values keep getting smaller and smaller until they peter out at that sharp point, and then they get bigger and bigger and bigger again until they hit that turning point, and then they get smaller and smaller and smaller again. And is it possible that this function cuts through at 27? Looks good. 27 and 0. So that's kind of what we had on my sketch. Now, of course, if I had to put some more tick marks there, maybe went up in 8s, 16, and 24, I would have improved the shape a little bit, but as long as all the features are labeled, we're good to go. And I think we more than demonstrated that we were able to use our first and second derivative features and information to piece together a pretty darn good sketch of this curve.